This is Chapter 14 of Astronomy 100. We're looking at the bizarre stellar graveyard. The topics in this chapter are dealing with white dwarfs, neutron stars, black holes, and something called gamma ray bursts. So let's look at white dwarfs first. What is a white dwarf, and what can happen to a white dwarf in a close binary system? This is the star Sirius A and the star Sirius B. They're obviously a binary star system, and this was taken with an X-ray telescope. White dwarfs, we know, are the remaining cores of dead stars, but electron degeneracy pressure supports them against gravity, so they don't totally collapse on themselves. We know that white dwarfs cool off as a red giant, and eventually a planetary nebula degrades into something where there's very little to no nuclear fusion going on. It's a much smaller star, much less massive star, and it goes down and to the right on the HR diagram. So it cools off and it grows dimmer. Here's a relative size of a white dwarf, about 1 solar mass in size, about the size of Earth. A 1.3 solar mass white dwarf is actually smaller. Apparently gravitational pull is bringing the remaining mass of the star in closer together. So quantum mechanics says that electrons have to move faster as they're squeezed into a very small space. And as a white dwarf's mass approaches 1.4 solar masses, its electrons must move at nearly the speed of light. But because nothing can move faster than light, a white dwarf can't be more massive than 1.4 solar masses. So this is called the white dwarf limit, also known as the Chandrasekhar limit. So there's a natural limit to how massive a white dwarf can be. So what happens to a white dwarf in a close binary system? Well, we kind of covered that in Chapter 13, but let's take another close look. So a star that started with less mass gains mass from its companion. Eventually, the mass-losing star will become the white dwarf, and then we see what happens next. The mass falling toward the white dwarf from its binary companion has a little bit of angular momentum. So the matter orbits a white dwarf in what's called an accretion disk. And so as you can see here, the star itself is actually spinning up a disk of matter. Friction between the orbiting rings of matter and the disk transfers angular momentum outward, and it causes the disk to heat up and glow. So this forms a very strange relationship between the larger companion star and the smaller white dwarf star spinning into a disk-shaped object. But the temperature of the matter that it's accumulating eventually becomes hot enough for nuclear fusion, and fusion begins suddenly and explosively, and it causes a nova. So this is another cause for a nova explosion, where fusion begins as the result of matter being pulled away by a companion star. That's only occurring, of course, in a binary star system. The nova system temporarily appears much brighter, and the explosion drives matter outward into space. So here's a pretty good example of a nova as a result of material being pulled away and the star exploding. There are two types of supernova. Massive star supernova, that's when an iron core of a massive star reaches the white dwarf limit and collapses into a neutron star. And then there are white dwarf supernova. That's carbon fusion suddenly beginning as a white dwarf reaches the close binary system, reaches the white dwarf limit. That causes a total explosion. So there are two types of supernova, and these are apparently the result of nuclear fusion. So here's one way to tell the difference between the two supernova types. Not that I'm going to ask you to do that, but just recognizing that there are two types of supernova, that's the important part of this topic. So supernovae, or supernovae, are much, much more luminous than novae, that's plural, about 10 million times. A nova takes hydrogen to helium, fuses, and we get a layer of accreted matter. The white dwarf is left intact. Whereas a supernova is a complete explosion of the white dwarf, sometimes leaving nothing behind. So there are differences in their light curves, which again I'm not going to ask you about, but their spectra will differ. Exploding white dwarfs don't have hydrogen absorption lines. So that's a slight difference between the two besides the light curves. So the essence of this topic is that supernova types, of which there are two, can be pretty readily identified by either one or both of these characteristics. So what is a white dwarf? It's the inert core of a dead star in which electron degeneracy pressure balances the inward pull of gravity. And what can happen to a white dwarf in a binary system? Well, matter from its binary companion can fall onto the white dwarf through an accretion disk, and the accretion of matter can lead to novae and white dwarf supernovae. Now let's look at neutron stars. What is a neutron star? How were neutron stars discovered? And what can happen to a neutron star in a close binary system? Here's a great picture of what we think is a neutron star. It's also on page 362 of your book. A neutron star is a ball of neutrons left behind by a massive star supernova. Degeneracy pressure of neutrons again supports a neutron star against gravity, so that's how it maintains its size. But electron degeneracy pressure goes away because electrons combine with protons, making more neutrons and producing neutrinos. So neutrons collapse to the center, forming a neutron star. So a neutron star is basically that, a big ball of neutrons. Could be about the same size as a small city. And this is how we think neutron stars were discovered. These pulses coming from this particular object were 1.337301 seconds apart. In other words, very, very fast pulses of certain intensities of light energy. Using this radio telescope in 1967, Jocelyn Bell noticed regular pulses of these radio emissions and that they were coming from a certain part of the sky. So eventually this phenomenon was called a pulsar, meaning a spinning neutron star. So here's an example of a pulsar at the center of the Crab Nebula, pulsing at 30 times a second. So this must be a very quickly moving neutron star. A pulsar is a neutron star that beams radiation along an axis. It doesn't have to be aligned with the rotation axis. And of course, we're not going to see it unless it sweeps across our view, as you can see here. It's kind of like a lighthouse. If the neutron star radiation is oriented so that we get a beam of light coming at us every X number of seconds, we'll be able to identify it as a neutron star. So why pulsars must be neutron stars? Well, the circumference of the star appears to be less than 60 kilometers in size. The spin rate is very, very fast, upwards of 1,000 times per second. So the surface rotation velocity of the star, somewhat over 60,000 kilometers per second or 36,000 miles per second, is very close to 20% the speed of light. So the rotation speed of the star is very, very fast. So let's look at what happens to a neutron star in a binary system. Well, just like before with a white dwarf, matter falling toward the neutron star forms an accretion disk. The accreting matter adds angular momentum, and that increases its spin, and episodes of fusion on the surface can lead to X-ray bursts. So apparently X-rays are the product of this beaming out from a neutron star. So matter accreting onto the neutron star can eventually become hot enough for helium to fuse, and the sudden onset of fusion produces these X-ray bursts. So neutron degeneracy pressure can no longer support the neutron star against gravity if its mass exceeds about 3 solar masses. So that's the limit, about 3 solar masses for a neutron star. So what is a neutron star? Well, it's a ball of neutrons left over from a massive star supernova supported by neutron degeneracy pressure. How were neutrons discovered? Beams of radiation from a rotating neutron star were sweeping through space like a lighthouse, making them appear to pulse. And these observations were the first evidence then for neutron stars. What can happen to a neutron star in a close binary system? Well, the accretion disk around a neutron star gets hot enough to produce X-rays, making the system an X-ray binary. Sudden fusion events periodically occur on the surface, and that produces the X-ray bursts. Next, let's look at black holes, gravity's ultimate victory. So, what is a black hole? What would it be like to visit a black hole? And do black holes really exist? Well, this is a very simple picture of what curvature of space looks like. Going in toward the center of this, obviously objects moving in toward the center are going to move faster and faster, and this would become a bottomless pit for anything moving into it. A black hole is an object whose gravity is so powerful light can't escape it. Some massive star supernovae can make a black hole if enough mass falls onto its core. So it is possible for some star to become a black hole if there's mass nearby. The surface of a black hole is the radius at which the escape velocity equals the speed of light. So the spherical surface that occurs at is called the event horizon. Again, light cannot escape inside the event horizon. And the radius, or the size of that event horizon, is known as the Schwarzschild radius. The event horizon of a 3 solar mass black hole is also about as big as a small city, but obviously much more massive and much more dense. So a black hole's mass strongly warps space and time in the vicinity of the event horizon. Going from A to B to C in these diagrams, you see that the larger the mass is of the object, the more it will curve space-time, exactly as you see on page 366. But nothing can escape from within the event horizon because nothing can go faster than light. And no escape means there is no more contact with something that falls in. It increases the hole's mass, changes its spin, but otherwise it loses the mass loses its identity. So a black hole can become bigger or more massive, but not necessarily larger. It just keeps bringing in the extra mass. The singularity, that's beyond the neutron star limit. No known force can resist the crush of gravity. So this is at a point where we don't know what happens after this mass is brought into a black hole and crushed. Gravity crushes all the matter into that single point. That's why it's called a singularity. So what would it be like to visit this black hole? Well, let's take the sun. If the sun shrank into a black hole, its gravity would be different only near the event horizon. So nothing is going to actually be sucked into the black hole. Instead, moving within or inside the event horizon, that's when things will happen. So light waves take extra time to climb out of a deep hole, and that leads to what's called a gravitational redshift. So as an object moves toward a black hole, any light reflecting off of or being emitted by the object will redshift. That's one thing that happens. Also, time passes more slowly for the object or the person, whatever the case might be, according to Einstein's theory of relativity. The closer you get to the event horizon, the slower time will pass for that person or object. Some other things. Any object moving in toward the event horizon will be squeezed vertically or squeezed horizontally and stretched vertically because of the tidal forces, the huge gravitational forces that the black hole is exerting. So do black holes really exist? Well, we think they do. Here's an example, or one place where we think it does, in the constellation Cygnus. There's an object there called Cygnus X1. So, need to measure mass? Well, we use orbital properties of the companion star, and we measure the velocity and distance of orbiting gas. It's a black hole if it's not a star and its mass exceeds the neutron star limit of 3 solar masses. Remember, that's the magic number, 3 solar masses. Something greater than that, and it's likely to be a black hole. So some X-ray binaries contain compact objects of mass exceeding 3 solar masses. They are likely to be black holes. So being able to measure all of these characteristics and come up with that answer is extremely difficult, but we think we have found one in the constellation Cygnus. So what's a black hole? Well, it's a massive object whose radius is so small that the escape velocity exceeds the speed of light. And of course, nothing can escape it. What would it be like to visit a black hole? Well, you could orbit a black hole like any other object if you stayed outside the event horizon. But near the event horizon, time slows down and tidal forces are very, very strong. Do they really exist? Well, some X-ray binaries contain compact objects too massive to be neutron stars. They're pretty sure that they are black holes. Finally, what causes gamma ray bursts? And we've talked about different or other forms of radiation being emitted. This is the last one, called gamma ray bursts. Here's a photograph of or a sequence of photographs showing what is believed to be a gamma ray burst, and this is what you see on page 373 at the top. Brief bursts of gamma rays coming from space were first detected in the 1960s. And of course, if it's a gamma ray burst, it has to be something which is emitting energy at a very, very high wavelength, very short wavelength. Observations in the 90s showed that many gamma ray bursts were coming from very distant galaxies. They must be among the most powerful explosions in the universe, maybe the formation of black holes. So observations showed that at least some gamma ray bursts are produced by supernova explosions, and others might actually be coming from collisions between neutron stars. So a collision of stars could actually produce these bursts. So what causes gamma ray bursts? Well, they're among the most powerful explosions in the universe, probably signifying the formation of black holes, but some of them might also be from colliding neutron stars. At least some gamma ray bursts come from supernova explosions in distant galaxies. So they are very, very energetic, very, very powerful explosions.